Well, so if this one issue aside, if we could only get rid of the weak force, then what would happen if the strong or electromagnetic forces were tinkered with?
Well, so one of the important things, of course, you have to remember when the universe was hot and young. So we had these stages of nucleosynthesis, the formation of the first elements. And that's essentially a game being played off between the strong force and electromagnetism, right? So those are the two forces that really matter in the early universe. And that can influence how elements form into hydrogen, helium, and then heavier elements. If you think about the nucleus of an atom, right? So what is the nucleus of an atom? It's a combination of protons and neutrons, okay? So in that ball, you've got the strong force that's pulling everything together, but you also have electromagnetism, which is trying to force all of those protons apart. And in fact, there's a huge amount of energy locked up in the nucleus of an atom due to the electromagnetic force in there. People sort of get this wrong. The atomic bomb was not a release of nuclear energy in the sense that it was from the strong force. The atomic bomb is powered by electromagnetism. When if you take a big nucleus and you separate it into two, you've got lots of charged particles close together and they whiz apart at high speed. That's what the energy release in an atomic bomb is. So there's a huge amount of energy in there. And so there's sort of like a balancing point, right? So the strong force has to overwhelm the electromagnetic force if that nucleus is going to stay stable. And the closer and closer that we bring these two forces together in terms of their strength, then the less stable nuclei become. So like we have in our periodic table, of course, we've got the elements and they've got isotopes. And there's this thing called the valley of stability, right? The combinations of protons and neutrons means that we have effectively stable versions of all the elements going up from hydrogen out to uranium. And that means is that in those nuclei, then what you've got is the strong force overwhelming electromagnetism, and it stays that way. But if you start to play around with those nuclei, you put in more or less neutrons, then you get radioactivity, right? So you get elements. So the nuclei basically decay in either alpha decay or even spitting out an electron or a positron. You get decays. So if you start to mess around with the relative strengths of electromagnetism and the strong force, one thing you can do very easily is you can erase the valley of stability. So this notion that most elements have a stable isotope, you can basically make that disappear. You can make everything radioactive. And that's probably a bad thing, right? Because if you imagine, again, molecular life, then you don't want to build your molecules out of things that are going to decay on relatively short timescales. You need your molecules to be stable over the time that you're going to use those molecules. So like the DNA inside your cells, you want that to be stable for a very long time until it's needed and separates and builds new DNA, etc. But if all elements become radioactive, then your DNA is made up of phosphorus and oxygen and all those kind of things, carbon. Then if they start popping off, then your DNA's ability to store information just completely disappears, right? So your molecules would break down. They would change from one molecule to another. That would be bad. But it turns out that you might say to yourself, oh, well, we can solve that problem, right? Well, all we do is we make the strong force even stronger. And what you do then is you broaden the valley of stability. So instead of there being like one stable carbon atom, your nature now is a choice of, say, 10, just changed by the mix of neutrons that you have. And you might say to yourself, well, what influence is that going to have? They're all carbon, right? The electrons don't care about how much mass is in the nucleus. They'll still behave like it's a carbon atom. But of course, when you form a molecule out of atoms, then the shape of that molecule depends upon the masses of each of those atoms. And so if you imagine that you're trying to build a molecule with carbon in there, and you have one carbon which is half the mass of another carbon atom, that means that when you construct those molecules, then they're all going to have different shapes, right? Because, I'll grab a light carbon atom and a heavy oxygen atom, etc., put them together. And again, you might say, well, who cares? The big problem is that your life cares, because we are molecular machines, and all molecules work by basically fitting together like jigsaw pieces, right? We saw this a lot with COVID, and how viruses have molecular receptors that fit into this kind of thing and that kind of thing. Those things have very well-defined shapes. And if you have a molecule with the wrong shape, it just doesn't work, okay? So by introducing more complexity, you can actually, again, run into the problem that you can't get the key features that you need for life by having more choice of atoms. We with complexity, again, thinking about more complex universes is harder than less complex universes. But it seems to me that, if you end up with a million different ways to construct the same molecule, that's bad for life, because you need things to be self-reproducing.
No, okay, this is very interesting. First, though, this is tangential, but you mentioned a common misconception about atomic bombs a few minutes ago. And so when you say that the atom bomb's explosive force comes from electromagnetism, it comes from the separation of positively charged protons. But for the force to have been generated by for the explosion to have been generated by the strong force, which is what people tend to think, that would mean the energy from the bomb would have to come from the protons themselves being ripped into quarks?
Not quite. Sorry, my microphone's got a bit dodgy here. Let me just fix that. Not quite. So this is so. Let's imagine how an atom bomb works. So we've all just seen Oppenheimer. So of course they didn't tell us much about the physics. But you've got like a big plutonium or uranium atom, and so in there's lots of protons which are close together, right? So what have you got? You put another neutron in there, okay, and then this splits into two nuclei, okay? So these two nuclei are no longer joined together by the strong force. They've got their own strong force inside, holding them together. And what you've got now is two strongly charged particles, two strongly charged nuclei, and they're a tiny separation apart. So you can calculate how much energy is in that situation. It's huge. So you basically, that then accelerates these guys away from each other. And that's the explosive power of the atom bomb. So the question is then, where did that come from? The packing of the protons and neutrons together to give you the big nucleus. And of course, that comes from massive stars. So the forces that put the nuclei together were gravity. Essentially, gravity squeezed things together hard enough that they could overcome electromagnetism, and the strong force could bind them together. Then you had them tied together. When you have an atom bomb, then you basically break that connection, and then they separate away. So of course the other one is the fusion bomb, right? So that's when you take deuterium and you combine deuterium into helium, and that is the strong force releasing energy. So that's when you've got two deuteriums, you combine them together, the strong force grabs hold of them, and they go into a lower energy state, and that releases a high energy photon. So fusion bombs are powered by the strong force releasing its energy, but the atomic bombs are powered by you breaking the strong force, and then the energy that's released is electromagnetism, which forces itself apart.
And
if that makes sense. Yeah.
Yes, it does. Deuterium is an isotope of hydrogen. So you're talking about hydrogen bombs when you're talking about fusion bombs?
Yes. Yeah. So yeah. So and you use deuterium because deuterium can fuse. Lone protons can't. So you can't stick two protons together to make a diproton because there's no such thing as a diproton in our universe. And you also can't stick two neutrons together. So what you start with is deuterium because they can fuse together because deuterium exists. That's another one of the fine-tuning questions, actually, is why we don't have diprotons and dineutrons in the universe. But that's a longer discussion about the lives of stars.
Okay, and then we don't have to dwell on this too long. I'm just curious, but is there a possible bomb that works the way that I described that generates energy from protons being pulled apart?
If you want to generate that kind of energy, what you want to do is you want to be putting protons together because that releases the strong force. I mean, if you pull if you want to shred a proton, you've got to put a lot of energy in. So this is what the Large Hadron Collider does, right? So you take two protons and you smash them together at high speed. That can rip the protons apart, but the universe into loose quarks. But the universe doesn't like loose quarks. Immediately, there's so much energy in those loose quarks is that they basically summon quarks out of the vacuum and they create these jets of material because there's so much potential there when you have a lone quark that it can pull other material out of seemingly nothing to create these quark jets. So there probably is, but I hope physicists don't go down the road of producing more powerful bombs. We've got enough at the moment.
Yes, no, perfectly fair. Then returning to the thread that we just left off, which is this idea of introducing more complexity by strengthening the strong force, and that in turn possibly precluding or limiting the possibility of life. Tell me if you think I'm on the right track here, but one way I see this, not just considering what would happen if suddenly the strong force were stronger, but if we think about what some primordial Earth, the way life is presumed to have arisen on Earth, forgetting like the panspermia hypothesis, things like that, is that through volcanic activity, through lightning, things like this, organic molecules just formed in the primitive soup and then gradually combined together over eons and mutated until they were self-replicating, until they formed primitive cell walls, methods of propulsion, this sort of thing. But if these primitive constituents were all the more complex, it would just be all the more unlikely that they could combine and form these self-replicating sort of structures, because they would be the constituents of the Earth would be so much more rarefied because there'd be so many more different types of things. Does that sound about right?
Yeah, I think so. I mean, you could imagine that life itself might be able to sort through the molecules, but once you've got more complex life, you've got molecular machines, etc. But if the choices are so huge that you're never going to find the right molecule, then that really does, start to really hinder what can actually happen.
Right. So as we lower complexity, we really eliminate the possibility for life. But as we increase it, it just becomes much, much, much more difficult.
Yeah, it becomes much harder to understand exactly how life could take advantage of that complexity. So as my colleague Luke Barnes, who I wrote the book with, he has this really nice thing that he has in his talks. He points out, if you said, bring the nuclear energy and the electromagnetic energy about the same, they're currently different by a factor of around 100,000, which is why a nuclear bomb is more powerful than a chemical bomb, etc. But if you bring them about the same kind of level, then you get all kinds of bizarre things happening. Like if you try to make a cake and you put all your ingredients in and you pop it in the oven, well, if nuclear energy transitions is about the same as electromagnetic energy transitions, then as you bake your cake, your your flour, etc., can transmute into lead. Right? So you can do nuclear reactions at thermal energy scales. So that sounds, again, like in that kind of situation, what would life do? Like, imagine you went out on a sunny day and sunlight started to turn the carbon in your skin into strontium or something. Whatever kind of nuclear kind of things you can imagine. It would seem that environment, even though there's more complexity there because you can do lots more stuff, maybe it's just too much. Maybe complexity works well when it's on a boundary, but when you have too much of it, you head into chaos rather than the stable environments that we need for life. But again, I'm sort of guessing at some level because the notion of trying to understand life in a more complex universe is hard to do because it's hard to even understand life in this universe as it is. But you can see that if you add in options, then maybe it works for some things, but for lots of other things, it's a negative.